At this time, it gives me great pleasure to introduce our commencement speaker, Dr. Susan Horowitz, the Rose C. Falkenstein Chair in Cancer Research and Distinguished Professor in our Department of Molecular Pharmacology. Dr. Horowitz is best known for discovering the mechanism of action of Taxol, a discovery which led to the approval and use of this drug to treat over 1 million patients for breast, ovarian, and lung cancer. She has been elected to the National Academy of Sciences, the National Academy of Medicine, and the American Academy of Arts and Sciences. Her dozens of awards include the Warren Alpert Foundation Award from Harvard Medical School, the Bristol Myers Squibb Award for Distinguished Achievement in Cancer Research, and the American Cancer Society's Medal of Honor. Please join me in welcoming Dr. Susan Horowitz.
Thank you, Dr. Spiegel, for your kind introduction and for giving me the opportunity to address this year's graduating classes. It is an honor. First, let me congratulate each of you and your families and your friends on this very special day. I recall vividly the excitement and awe that scientists experienced when Watson and Crick published The Structure of DNA in 1953 and revealed that its nucleotide sequence, our genetic code, was in the form of a 3-dimensional double helix. Who could have imagined at that time that today one of our goals would be to sequence DNA from tumors of all cancer patients entering a modern hospital, or that we would be discussing pros and cons on many different levels of editing DNA. I would not even try to imagine the advances in basic biomedical sciences, medical diagnosis, and therapeutics that you will experience during your professional careers. I believe that you are entering an era that will be characterized by remarkable advances in experimental, in translational, and clinical science. We live in a multidisciplinary world in which scientists and physicians integrate biological and chemical sciences with a variety of new and rapidly evolving inputs from stem cell biology, epigenetics, tissue engineering, computer science, and mega data analysis, among other areas, to promote the health and well-being of human beings throughout the world. Every morning when I come to work and walk through the lobby of the Forsheimer building, I see the motto, "Science at the heart of medicine." That motto sets me up for the day because I know that major progress in the treatment of serious disease will come from a greater understanding of human physiology and chemistry. Since my interests are in drug development therapeutics for the treatment of cancer, I have selected a few examples to illustrate my thoughts. We could go back about 100 years to 1914, when Theodore Boveri, the German cytologist, proposed that cancer can be caused by abnormalities in chromosomes, based on studies that he performed in sea urchin eggs. However, let's start in 1960, when a graduate student, David Hungerford, working with Peter Noel, observed that cells from patients with chronic myelogenous leukemia, or CML, often contained an abnormal small chromosome. This was named the Philadelphia chromosome after the city in which they worked. 13 years later, Janet Rowley discovered that the Philadelphia chromosome was generated during the breakage and fusion of two chromosomes, a phenomenon called translocation. Dr. Rowley, who in later years became a good friend of mine, told me that when she first observed the translocation between two chromosomes, she had 4 young boys and was working 3 days a week at the University of Chicago Medical School. When Janet applied to medical school in 1944, she had to wait an extra year because the quota for women, 3 spots in a class of 65, was already filled. After medical school, she worked in a clinic for children with developmental disabilities, and it was discovered at this time that children with Down syndrome had an extra copy of chromosome 21. Dr. Rowley became fascinated by the involvement of genetics, and particularly chromosomal locations, in the genesis of cancer. During the succeeding decades, Janet Rowley's initially controversial hypothesis that chromosomal translocations cause specific cancers emerged as an established, critically important fact in tumor biology. She was an exceptional role model for scientists in general and underrepresented women in particular, who coupled basic genetic analysis to human disease. Progress in science often depends on the development of new technologies. The ability to observe translocations became possible with the introduction of chromosome banding. The translocation underlying the Philadelphia chromosome produced the human CML protein known as BCR-ABL, which is sufficient to cause the leukemia. The BCR-ABL protein is a persistently active protein kinase that drives unchecked cell division. Brian Drucker, an oncologist, led an intensive effort to find a drug that would block the enhanced activity of BCR-ABL and thereby subdue CML. Together with chemists from Novartis, Gleevec, a small molecule that selectively targets the active site of BCR-ABL, thereby ablating kinase activity, was developed. The administration of Gleevec to patients with CML stops the progression of a fatal disease and enables 90% of CML patients to have a normal, disease-free lifespan. In the absence of Gleevec treatment, almost 50% of CML patients die during the first year after diagnosis. The development of Gleevec is a truly beautiful example of the importance of basic and clinical scientists, physicians, and pharmaceutical companies working together to make paradigm-shifting advances in cancer treatment. In my laboratory, we've been concerned with understanding the mechanisms by which anti-tumor drugs kill cancer cells. In 1977, when I was a young faculty member, I received a letter from the National Cancer Institute requesting that I determine how a new drug, Taxol, that had been isolated from the bark of the yew tree, shrunk tumors in mice. I was attracted to the drug because it is architecturally complex, a truly intriguing molecule. At that time, almost 40 years ago, Peter Schiff was a new graduate student in my lab searching for a thesis project. Peter and I requested 10 milligrams of Taxol from the National Cancer Institute, and I made it clear that if after 1 month the results did not seem interesting, we would have to find a new project. As it turned out, we discovered a new mechanism of action for an anti-tumor drug, the stabilization of microtubules, an important component of the cytoskeleton that is necessary for normal cell division. No one was particularly interested in what we were doing, and we could not predict that the drug would be useful in the clinic. But today, it has been given to over 1 million patients with ovarian, breast, and lung cancers. When we started the project, there was a single paper in the literature about Taxol, the original report describing its isolation and structural determination. As of last night, there were 29,962 published papers that had the word Taxol or its generic name paclitaxel in their title. It all started in the laboratory with a simple basic question: how does Taxol kill tumor cells? The right, simple question can often produce meaningful results that can have a major impact. A single patient can confront you with a new question that will open your eyes to a new paradigm. The development of both Gleevec and Taxol was a slow process, taking much too long to reach patients. As we move forward with new technologies, such as computer-designed drugs and large databases, we anticipate that drugs developed in the laboratory will move into the clinic at an accelerated rate. With our continuing and newly expanded relationship with Montefiore Medical Center, the Einstein community is in a perfect position to fully participate in this process. For you to be part of this process, which you must be, it is incumbent upon you to appreciate the necessity of remaining curious and thinking creatively in order to assimilate and contribute new knowledge through careful observation and original basic, translational, and clinical research. We need a large pool of talented, critically thinking scientists and physicians who are willing to solve difficult problems and appreciate both the necessity and rewards of lifelong learning. In today's world, if you are not intellectually nimble, you will soon become a dinosaur. In 1915, our namesake Einstein made the following statement: "One should not pursue goals that are easily achieved. One must develop an instinct for what one can just barely achieve through one's greatest efforts." Einstein followed this precept when 100 years ago he presented his theory of general relativity. This past February, a faint chirp was heard which verified an unproven portion of Einstein's theory. Gravitational waves were detected for the very first time. Few have Einstein's brilliant mind, and none of us want to wait 100 years for verification. But we can all add substance to the body of scientific and medical literature through careful experimentation and observation, and importantly, transmit our knowledge to the next generation. I urge you all to participate in making advances in biomedical science a reality that will benefit the health, well-being, and quality of life for all humanity. But there is much more to the motto than science and medicine. There is heart. As I have become older, I have realized the importance of being kind, Not just a smile or a nod, but genuine concern and compassion for others. Whether you spend your time in the laboratory or the clinic or both, there is need to listen to your students, to your patients, to your colleagues, and to your children with genuine interest and concern. Although the advances that have been made in technology are greatly admired, they can never replace the empathy that can develop between humans or within a community. I have always been very proud of being a faculty member at Albert Einstein, particularly because it has been blind to race, religion, gender, and political persuasion in the hiring of its faculty, in the selection of students and fellows, and in the treatment of patients. This has made it a very special place for me to work, and I hope also for you to be students. I would like to end with a few verses from one of my favorites, Dr. Seuss. Congratulations, today is your day. You're off to great places, you're off and away. You have brains in your head, you have feet in your shoes. You can steer yourself any direction you choose. You're on your own, and you know what you know, and you are the ones who'll decide where to go. So, be your name Buxbaum or Bixby or Bray, or Mordecai Ali Van Allen O'Shea, you're off to great places. Today is your day. Your mountain is waiting, so get on your way. Thank you, and best of luck to each of you.